Artificial intelligence goes for beginner by knowledge and information. In this video, we will discuss about supervised learning. Supervised learning is a machine learning technique where a model is trained using labeled data. In supervised learning, we have a dataset that consists of input features, also known as independent variables or predictors, and their corresponding output labels, also known as dependent variables or targets. The goal is to train a model that can learn the mapping between the input features and the output labels, allowing it to make predictions or classifications on new, unseen data. The process of supervised learning involves the following steps. One. Data collection. Collect a dataset that contains examples of input features along with their corresponding output labels. The dataset should be representative of the problem you want to solve. Two. Data preprocessing. Clean the dataset by handling missing values, removing outliers, and transforming the data into a suitable format for training. Three. Feature selection, engineering. Select relevant features from the dataset or create new features that can improve the performance of the model. Four. Model training. Split the dataset into a training set and a validation set. Use the training set to train the model by presenting the input features and their corresponding output labels. The model learns the underlying patterns in the data and adjusts its internal parameters to minimize the error between the predicted output and the true output. 5. Model evaluation. Evaluate the performance of the trained model using the validation set. Common evaluation metrics depend on the specific problem, such as accuracy, precision, recall, F1 score, or mean squared error. The choice of the metric depends on whether the task is classification or regression. Six. Model tuning. Adjust the hyperparameters of the model to improve its performance. Hyperparameters are settings that are not learned by the model itself but are set by the user before training. Examples of hyperparameters include learning rate, regularization strength, and the number of hidden layers in a neural network. 7. Model deployment. Once you are satisfied with the model's performance on the validation set, you can deploy it to make predictions on new, unseen data. Common algorithms used in supervised learning include linear regression, logistic regression, support vector machines, decision trees, random forests, gradient boosting, and neural networks. The choice of algorithm depends on the nature of the problem and the characteristics of the dataset. It's important to note that supervised learning requires labeled data, which means you need a dataset where the correct answers or labels are already known. In some cases, obtaining labeled data can be costly or time-consuming. 8. Overfitting and underfitting. Overfitting occurs when a model learns the training data too well, capturing both the underlying patterns and the noise present in the data. As a result, the model may fail to generalize well to new, unseen data. Underfitting, on the other hand, happens when the model is too simple and fails to capture the underlying patterns in the data. Balancing between overfitting and underfitting is a crucial aspect of supervised learning. Techniques like regularization, cross-validation, and adjusting the complexity of the model can help mitigate these issues. Nine. Cross-validation. Cross-validation is a technique used to assess the performance and generalization of a model. It involves splitting the dataset into multiple subsets or folds, and training the model on a combination of these folds while evaluating it on the remaining fold. This process is repeated several times, with different folds used for training and testing in each iteration. Cross-validation helps estimate how well the model is expected to perform on unseen data and aids in selecting the best hyperparameters. Ten. Classification versus regression. Supervised learning can be categorized into two main types: classification and regression. Classification tasks involve predicting discrete labels or classes, such as identifying whether an email is spam or not. Regression tasks, on the other hand, involve predicting continuous numerical values, such as predicting house prices based on features like area, location, and number of bedrooms. 11. Bias-variance trade-off. The bias-variance trade-off is a fundamental concept in supervised learning. Bias refers to the error introduced by approximating a real-world problem with a simplified model, while variance refers to the model's sensitivity to the training data. A high-bias model may underfit the data, while a high-variance model may overfit the data. Finding the right balance between bias and variance is crucial to achieve good generalization performance. 12. Ensemble learning. Ensemble learning involves combining multiple models to improve predictive performance. By training multiple models and aggregating their predictions, ensemble methods can often achieve better accuracy and robustness compared to individual models. Common ensemble techniques include bagging, e.g., random forests, and boosting, e.g., gradient boosting. These concepts provide a foundation for understanding supervised learning. The field of machine learning is vast, and there are many advanced algorithms and techniques that build upon these fundamentals. It's an exciting area that continues to evolve and find applications in various domains. 13. Transfer learning. Transfer learning is a technique where knowledge gained from training one model on a specific task is transferred or applied to a different but related task. Instead of training a model from scratch, transfer learning leverages the pre-trained model's learned features, which can help improve the performance of the model on the new task, especially when the new task has limited labeled data. 14. Bias and variance analysis. When evaluating the performance of a supervised learning model, it's important to analyze the bias and variance components. Bias refers to the error introduced by the model's assumptions or limitations, while variance refers to the model's sensitivity to small fluctuations in the training data. Understanding the bias-variance trade-off can guide the selection of appropriate models and help diagnose issues like underfitting or overfitting. 15. Regularization. Regularization is a technique used to prevent overfitting in models. It involves adding a penalty term to the loss function during training, which encourages the model to have smaller weights or simpler representations. Common regularization techniques include L1 and L2 regularization, which add the absolute or squared values of the weights to the loss function, respectively. 16. Imbalanced data. Imbalanced data refers to a situation where the distribution of classes in the labeled dataset is uneven, with one or more classes being underrepresented compared to others. This can pose challenges for supervised learning, as the model may become biased towards the majority class. Techniques like oversampling the minority class, undersampling the majority class, or using class-weighted loss functions can help address this issue. 17. Active learning. Active learning is a strategy where the model actively selects and queries the most informative or uncertain instances from an unlabeled dataset to be labeled by an expert. By iteratively selecting the most valuable samples to label, active learning can reduce the annotation effort required while maintaining or improving the model's performance. 18. Time series forecasting. Time series forecasting is a specific type of supervised learning where the input data is organized in a sequential manner based on time. The goal is to predict future values or patterns based on past observations. Various techniques, such as autoregressive models, moving averages, and recurrent neural networks, RNNs, can be used for time series forecasting tasks. These concepts provide further insights into the different aspects and challenges of supervised learning. It's important to explore and adapt these techniques based on the specific problem and dataset at hand to build accurate and reliable models. (19) Hyperparameter optimization. Hyperparameters are parameters that are not learned by the model itself during training, but rather set by the user before training. These parameters control aspects such as the learning rate, regularization strength, number of hidden layers, and other settings that influence the model's behavior. Hyperparameter optimization techniques, such as grid search, random search, or more advanced methods like Bayesian optimization or genetic algorithms, are used to systematically search for the best combination of hyperparameters that maximize the model's performance. (20) Feature importance. Feature importance refers to the measure of the impact or relevance of each input feature on the model's predictions. Understanding feature importance can help identify which features contribute most significantly to the model's decision-making process. Techniques like feature importance scores derived from decision trees, e.g., Gini importance or permutation importance, or feature importance from regularization, e.g., L1 regularization's tendency to encourage sparsity, can be used to assess the importance of different features. (21) Handling missing data. Real-world datasets often contain missing values, which can adversely affect the performance of a supervised learning model. Various strategies can be employed to handle missing data, such as removing instances with missing values, imputing missing values with statistical measures, e.g., mean, median, or using more advanced techniques like interpolation or regression-based imputation. 22. Multi-class classification. In addition to binary classification, where there are only two classes, supervised learning can also address multi-class classification problems, where there are more than two classes to be predicted. Algorithms like logistic regression, support vector machines, random forests, and neural networks can be extended to handle multi-class classification tasks using techniques like 1vs REST or softmax activation. 23. Evaluation metrics. The choice of evaluation metrics depends on the specific problem and the nature of the output labels. For classification tasks, common evaluation metrics include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve, ROC AUC. In regression tasks, metrics like mean squared error, MSE, mean absolute error, MAE, or R-squared can be used to evaluate the model's performance. 24. Online learning. Online learning, also known as incremental learning or streaming learning, is a variant of supervised learning where the model is continuously updated and adapted to new data points as they arrive in a sequential manner. This approach is particularly useful when dealing with large or streaming datasets that cannot fit entirely into memory or when the data distribution changes over time. 25. Data augmentation. Data augmentation is a technique used to artificially increase the size of the training dataset by creating new training examples from the existing data. This can involve applying transformations such as rotation, scaling, flipping, or adding noise to the input data, while keeping the labels unchanged. Data augmentation helps to improve the model's generalization and robustness by exposing it to a wider variety of training examples. 26. Ensemble methods. Ensemble methods combine predictions from multiple models to make a final prediction. This can help improve the overall accuracy and robustness of the predictions by leveraging the diversity of multiple models. Examples of ensemble methods include bagging, where multiple models are trained on different subsets of the training data, and then their predictions are averaged or combined, and boosting, where models are trained sequentially, with each subsequent model focused on correcting the errors made by the previous models. (27) Semi-supervised learning. In semi-supervised learning, the training dataset contains both labeled and unlabeled examples. The idea is to leverage the additional unlabeled data to improve the model's performance. The model learns from the labeled data as well as the underlying structure or patterns present in the unlabeled data. Techniques like self-training, co-training, and generative models can be used in semi-supervised learning. 28. Cost-sensitive learning. Cost-sensitive learning takes into account the varying costs or misclassification penalties associated with different types of errors. In some applications, misclassifying certain instances may have more severe consequences than others. Cost-sensitive learning adjusts the learning algorithm to minimize the overall cost of misclassifications, rather than just focusing on accuracy. It assigns higher weights or penalties to the misclassification of certain classes or instances. Bias-variance trade-off. The bias-variance trade-off is a fundamental concept in supervised learning. Bias refers to the error introduced by approximating a real-world problem with a simplified model, while variance refers to the model's sensitivity to the training data. A high-bias model may underfit the data, while a high-variance model may overfit the data. Finding the right balance between bias and variance is crucial to achieve good generalization performance. 29. Model interpretability. Model interpretability refers to the ability to understand and explain the decision-making process of a supervised learning model. Interpretable models provide insights into how the model arrives at its predictions, which is crucial for building trust and understanding the model's behavior. Techniques like feature importance analysis, partial dependence plots, and model-agnostic interpretability methods, e.g., LIME or SHAP, help in interpreting and explaining the model's predictions. (30) Active feature selection. Active feature selection is a technique that involves actively selecting the most informative or relevant features from a larger set of available features. This helps reduce the dimensionality of the data and focus on the most discriminative features, which can lead to improved model performance, faster training, and better interpretability. In next video we will discuss more about supervised learning. Thanks for watching. Please like, share and subscribe.